Have you ever wondered how a slight temperature shift in one ocean can somehow cause a massive, devastating drought thousands of miles away? Or, why it snows exactly where it does, and why the tropics are just perpetually warm? Well, let's dive right into this explainer. Today, we're deconstructing the mechanics behind global weather patterns, using our sources to see the Earth not just as a planet, but as this giant, deeply interconnected, breathing machine. Here is how we're going to break this down today. First, our layered atmosphere. Then, the solar heat engine. Third, pressure, wind, and spin. Fourth, global wind circulation cells. And finally, number 5, El Niño and global monsoons. All right, let's kick things off with section 1, our layered atmosphere. So think of the troposphere as the stage where all the action happens. It's the lowest layer, it holds pretty much all life, and absolutely all of our weather occurs right here. And what's really interesting is that it actually gets colder as you go up. It's also way thicker at the equator, about 18 kilometers thick, because all that intense heat causes the air to expand. But as soon as you cross into the stratosphere right above it, the rules completely flip. The stratosphere actually gets warmer the higher you go. Why? Because the ozone layer is up there, just absorbing massive amounts of high-energy UV radiation from the sun and turning it into heat. Now, going back to that weather-filled troposphere for a second, here's a crazy specific number for you. For literally every single kilometer you go up in the troposphere, the temperature drops by exactly 6.5 degrees Celsius. In climatology, they call this the environmental lapse rate. And it's exactly why you can have snow-capped mountain peaks right in the middle of a tropical region. If you keep ascending past the stratosphere, you hit the mesosphere. This is where the gas density increases just enough to cause incoming meteors to burn up from friction, giving us those beautiful meteor showers. Keep going and you're in the burning hot thermosphere and eventually the exosphere. But, where does Earth actually end and space begin? People usually say 100 kilometers, but actually, NASA now defines the Kármán line, the official boundary of outer space, as starting at just 50 kilometers up. Moving right along to section 2, the solar heat engine. Think about this. If the sun heated the Earth perfectly evenly, we would literally have zero weather. None. The whole system runs because the heat we receive is totally uneven, dictated by our elliptical orbit, our tilted axis, the length of the day, and atmospheric transparency. But the absolute biggest factor is the angle of incidence. The sun's vertical rays hit the equator dead on, delivering this intense concentrated heat. But up at the poles, those rays are slanted. They have to travel through way more atmosphere and spread their energy over a much wider area, which makes the heat significantly weaker. And keep in mind, not all of that solar fuel actually gets absorbed by the Earth. Whatever isn't absorbed gets bounced away, and we measure this using something called albedo. It's just a scale from 0 to 1 that tells us how reflective a surface is. Dark surfaces, like our massive deep oceans, have a very low albedo near 0. They are soaking up huge amounts of solar heat. On the flip side, bright white things like fresh snow or thick clouds have a super high albedo near 1. They act like giant mirrors, reflecting all that precious solar energy right back out into space. So, when you combine that uneven solar heating with all that reflection, you end up with very distinct global heat zones. We're operating with a massive heat surplus in the torrid or tropical zone right at the equator. Then we've got moderate energy in the temperate zones and a major heat deficit in the frigid zones near the poles. The planet is basically just constantly trying to balance this energy budget. Which brings us to section 3, pressure, wind, and spin. How does the Earth balance that budget? Wind. And it all starts with the pressure gradient force. When air gets heated, it expands and rises, right? That leaves behind an empty space, a zone of low pressure at the surface. On the other hand, cold, heavy air sinks, piling up to create high pressure. Wind is literally just the atmosphere rushing horizontally across the surface from high to low pressure to balance the scales. But wait,
The Earth is constantly spinning from west to east, so this rushing wind doesn't get to just travel in a neat straight line. It gets twisted by something called the Coriolis force. It's this apparent deflecting force that yanks moving air to the right in the northern hemisphere and to the left in the southern hemisphere. It is the exact reason why massive storm systems and hurricanes spiral the way they do.
All right, Section 4, Global Wind Circulation Cells. When you take that extreme equatorial heat, the pressure changes, and that Coriolis spin, you get these massive interconnected global loops. The Hadley cell is the big one. Intense solar heat at the equator forces warm, moist air to rise up. It hits the ceiling of the troposphere, cools off, and gets pushed out toward the poles. By the time it hits 30 degrees latitude, it's dense enough that it plummets back down to Earth, creating high pressure. Then it rushes right back to the equator as the trade winds. It's a massive conveyor belt. Now, the Hadley cell at the equator and the polar cell at the very top and bottom of the globe are what we call thermally direct cells. They are powered directly by the sun's intense heat, or the extreme lack of it. But sandwiched right between them is the Ferrel cell. The Ferrel cell is thermally indirect. It's not driven directly by the sun. It's driven entirely by the mechanical mixing of those other surrounding air masses. Picture that mixing zone, right around 60 degrees latitude. It is a chaotic, turbulent place. You have relatively warmer air migrating up from the subtropics, and it just violently crashes into this freezing, dense air spilling out from the poles. This collision forces the warmer air upward, carving out a huge low-pressure zone. This messy mixing process creates turbulent waves of air called eddies, and it's exactly what drives those massive mid-latitude cyclones that dump storms all over North America and Europe. Okay, so we've mapped out how the normal machine works, right? We've got our neat pressure zones and our spinning circulation cells, but what happens when someone or something throws a massive wrench into the gears, specifically the giant watery gears of the Pacific Ocean? That brings us to our final section, number 5, El Niño and global monsoons. Normally, trade winds act like a giant fan, pushing warm surface water westward across the Pacific. This brings reliable, healthy rain to Australia and helps drive the vital Indian monsoon. During a La Niña year, this whole system just goes into a 150% overdrive. Way stronger winds, heavy flooding in Australia, and an intensely strong monsoon in India. But during an El Niño event, that giant fan just dies. The winds weaken, and all that warm water sloshes right back towards South America. It flips the entire global pattern upside down. Suddenly, you have floods in South American deserts, severe, devastating droughts in Australia, and a drastically weakened monsoon for India. And it gets weirder, because there's this fascinating wild card called Modoki, which actually means middle in Japanese. In a Modoki event, the trade winds aren't strong enough to push the warm water all the way to Australia, but they don't completely collapse either. So this giant warm pool just stalls right in the dead center of the Pacific Ocean. It creates a bunch of rain in the middle of nowhere while causing terrible high-pressure droughts in both Australia and South America at the same time. And yet it still weakens the Indian monsoon. Because these events can literally make or break a country's agriculture and economy. Climatologists watch them like hawks using the ENSO index. Basically, they measure the atmospheric pressure difference between Darwin, Australia, and Tahiti in the Central Pacific. If there's a really high pressure difference, it means those normal winds are blowing strong, so brace for a flood-inducing La Niña. A low difference, the winds are dying, which is our early warning system that a drought-inducing El Niño is on the horizon. But here's a really cool twist for India. They actually have a backup engine. It's called the Indian Ocean Dipole, or IOD. If the Arabian Sea gets warmer than usual, it creates a positive IOD. This actually strengthens the monsoon winds, pulling moisture toward India and totally mitigating those terrible El Niño droughts, which is exactly what saved the day back in 1997. On the flip side, though, a negative IOD pulls all that precious moisture away toward Indonesia, leaving India dry. So, as we wrap up this explainer, we've really seen how intricately connected this global weather engine is. From that precise 6.5-degree temperature drop in the troposphere to the spin of the Coriolis force, right down to the sloshing warm waters of the Pacific. It leaves us with a pretty massive question. If a simple temperature shift in one single ocean can cause deadly bushfires in Australia and totally disrupt vital monsoons in India, what other distant dominoes are just waiting to fall as the Earth's temperatures continue to shift? Thanks for exploring the mechanics of our